Hello, this is TCG and welcome to the sixth lecture for the CompTIA Security Plus 601 exam. Let's get started. Authentication is a critical aspect of cybersecurity, ensuring that the users are who they claim to be and prevents unauthorized access to the organization's resources. Directory service. A directory service is a centralized database that stores information about users, devices, and resources within a network. It is used for authentication and authorization. Some examples are as follows. Active Directory. It is a Microsoft directory service for Windows domain networks. Lightweight Directory Access Protocol or LDAP. It is a protocol used to access and manage directory information. Federation. Federation involves the sharing of identity information across multiple services or organizations, allowing users to access resources using credentials from their home organization. Attestation. Attestation refers to the process of verifying the integrity of a system, ensuring that it has not been tampered with. It is usually done using a key, token, or a code that exists on the system. Authentication via SMS. Authentication via SMS. Authentication via SMS involves sending a one time password or an OTP to the user's phone via SMS. This is like a third input field after username and password, adding an additional layer of security and authentication beyond username and password. It is slightly risky since SMS can be intercepted and phones can be compromised. Also note that SMSs are not encrypted by default. Push notification authentication. This sends a push notification to the user's mobile device, prompting them to approve or deny the login attempt. It is easy and quick for users to approve logins and is harder to intercept compared to SMS. Google uses this kind of authentication. Authentication apps. Authentication apps generate time-based or counter-based OTPs. Users must enter the OTP from the app to complete the authentication process. Some famous examples for authentication apps are Google Authenticator and Microsoft Authenticator. OTPs are generated locally on the device and not transmitted over the network. Hence, this works without network connectivity and is safe. Time-based OTP. Time-based OTP is generated based on the current time and a shared key. It changes at regular intervals, typically every 30 seconds. Authentication via phone call. Authentication via phone call involves calling the user and providing a verbal OTP or asking the user to confirm the login attempt. It is useful for users who may not have a smartphone or a data service. It is more secure than SMS but still vulnerable to social engineering and phishing attacks. Static codes. Static codes are pre-generated codes that a user can use for authentication. These are often used as backup codes for two-factor authentication. It is useful when other authentication methods are unavailable and is easy to use and distribute. Smart cards. Smart cards are physical cards embedded within a chip that stores authentication data. They are used with a card reader to authenticate users. They are difficult to duplicate and can store cryptographic keys and can be used for physical access control as well. The only downside with smart cards is that they can be stolen or damaged. Biometrics. Biometrics refer to the use of physical and behavioral characteristics for identifying and authenticating individuals. This method of authentication offers a high level of security as these characteristics are unique to each individual. Now let us talk about the factors used for biometric authentication. Fingerprint recognition. It uses the unique patterns of ridges and valleys on a person's fingertip. It is highly accurate, easy to use, and is used in smartphones, access control systems, and time and attendance systems. Retina scanning. It analyzes the unique pattern of blood vessels in the retina located at the back of the eye. It is also highly high accurate, gives high security, and is used in high security areas, government, and military installations. Iris recognitions. It uses the unique patterns in the color ring surrounding the pupil of the eye. It is used in airports, national ID programs, and border control. Voice recognition. Voice recognition authentication identifies individuals based on unique vocal characteristics such as pitch, tone, and cadence. It is used in call centers, mobile banking, and voice activated systems. Facial recognition. These systems analyze facial features such as distance between eyes, nose, and mouth. They're used in surveillance, social media tagging, and smartphone unlocking. They are convenient and can be used in existing cameras. Gait analysis. Gait analysis involves identifying individuals based on the unique way of walking. It is non intrusive and can be observed from a distance. Vein pattern recognition. It uses the unique patterns of veins in the hand or finger. It is highly accurate and difficult to forge and is used in banking, healthcare, and secure facilities. Biometric acceptance rates. While evaluating biometric systems, three key metrics are used to measure the effectiveness and accuracy. False acceptance rate, or FAR. This is the rate at which a biometric system incorrectly accepts an authorized user. A high FAR indicates a security risk, as unauthorized users can gain access. False rejection rate, or FRR. This is the rate at which a biometric system incorrectly rejects an authorized user. A high FRR can be frustrating for legitimate users as they are denied access. Crossover error rate. It is the point at which FAR and FRR are equal. It is a common measure of the overall accuracy of a biometric system. A lower CER indicates a more accurate and reliable biometric system. Multi-factor authentication, or MFA. MFA is a security mechanism that requires users to provide two or more verification factors to gain access to a resource, be it an application, online account, or VPN. By combining multiple forms of authentication, MFA significantly enhances security compared to single factor authentication, which typically relies on just a password. The AAA framework, which stands for Authentication, Authorization, and Accounting, is a security framework used to control access to resources, enforce policies, and audit usage. Authentication. Authentication verifies the identity of a user, device, or an entity before allowing access. This can involve something that you know, which may be a password or PIN, something you have, which may be a smart card or security token, or something you are, which includes biometric factors like fingerprints and facial recognition. Authorization. It determines what an authenticated user is allowed to do. This involves defining permissions and roles to restrict access to certain resources and actions. Accounting. Accounting tracks and records the user activities. This includes logging access times, duration of sessions, and resources accessed, which is crucial for auditing and compliance. Authentication on the cloud versus authentication on premises. Authentication on the cloud is done by a third party on a platform on the internet, while on premises authentication is done locally. Management and external access is tedious on premises but can be done quickly on the cloud. Disk redundancy. Disk redundancy helps ensure data availability and reliability even in the event of hardware failure. This can be achieved through several methods, which we will discuss as follows. Geographic disposal. Geographic disposal involves storing copies of data in multiple physically separate locations. This strategy enhances data availability and disaster recovery capabilities. It protects against data loss due to natural disasters, power outages, and other localized incidents, and ensures data remains accessible even if one location fails. Multipath input-output. Multipath I/O refers to the use of multiple physical paths to transfer data between a computer system and its storage device. This approach enhances redundancy and performance. It provides multiple pathways for data to travel between storage and systems, reducing the risk of a single point of failure. It also helps in load balancing by distributing data transfer loads across multiple paths, improving overall system performance. RAID, or redundant array of independent disks. RAID is a technology that combines multiple physical drives into a single logical unit to improve performance, redundancy, or both. There are several levels of RAID, each offering different trade offs between performance, data protection, and storage efficiency. RAID level 0, known as stripping. In RAID level 0, data is split into blocks and written across all the disks in the array. This improves read write performance, but there is no redundancy, which means if one disk fails, then all data of that disk is lost. RAID level 1 mirroring. In RAID level 1, the data is duplicated on two or more disks. It gives high data redundancy and fault tolerance, but the storage capacity is halved due to the cost of duplication. RAID level 5, known as oh god, RAID level 0, also known as stripping. In RAID level 0, the data is split into blocks and written across all the disks in the array. This improves read write performance but offers no redundancy, which means that if one disk fails, all the data of that disk is lost. RAID level 1, which is known as mirroring. In RAID level 1, the data is duplicated on two or more disks, which offers high data redundancy and fault tolerance, but the storage capacity is halved or maybe higher due to the cost of duplication. RAID level 5, known as striping with parity. In this case, data and parity information are striped across three or more disks. This offers a good balance of performance, storage efficiency, and redundancy, but has slower performance due to parity calculations and can survive a single disk failure at max. RAID level 6, known as stripping with double parity. It is similar to RAID 5 but has double parity information. That means it can survive up to two disk failures, which leads to better fault tolerance. RAID level 10, which is essentially a mix of RAID level 1 and RAID level 0, mirroring and striping. It combines both RAID 1 and RAID 0 and offers high performance and fault tolerance, but is expensive due to the need for double the number of disks. RAID level 50, which is RAID level 5 and RAID level 0. It combines multiple RAID 5 arrays into a RAID 0 array, which improves performance and fault tolerance, but has a complex setup and high management costs. RAID level 60, which combines multiple RAID 6 arrays into a RAID 0 array. It also has a high fault tolerance and performance, but is even more complex than RAID 50 and has even higher costs. Network redundancy. Load balancing. Load balancing distributes network traffic across multiple servers or paths to optimize resource use, maximum throughput, and minimum downtime and response time. It enhances the availability and reliability of applications and services by preventing any single server from becoming a bottleneck. Routes incoming request to the least document loaded or most appropriate server. It continuously checks the health of servers and redistributes traffic away from unhealthy servers. It also allows for easy addition of new servers to handle increased traffic. NIC teaming. NIC teaming, also known as link aggregation or bonding, combines multiple network interface cards (NICs) into a single logical interface. This provides redundancy and increased bandwidth. Multiple NICs provide failover capacity even if one NIC fails, and aggregates bandwidth of all NICs, resulting in a higher throughput. Port aggregation. Port aggregation, also known as link aggregation or Ether channel, combines multiple physical ports into a single logical link to increase bandwidth and provide redundancy. It maintains network connectivity even if one or more port fails, and allows easy addition of new ports into the aggregated group. Switch redundancy. Switch redundancy involves using multiple switches to ensure network availability in case of a switch failure. This can be achieved through various protocols and architectures. Some of them are the Spanning Tree Protocol or STP, which prevents loops in a network while it by blocking some paths and using them only when the primary path fails. VS a virtual system switch system which combines two physical switches into a single logical switch, providing redundancy and increased capacity. Power redundancy. Power failure is directly translated into downtimes, which translates further into financial losses, which is why we need to make sure that supply is not interrupted. UPS or uninterruptible power supply. UPS is a device that provides emergency power to a load when the input power source fails. It ensures that critical equipment continues to operate during short term power outages and allows for safe shutdown or switchover to backup systems. The three major types of UPS that we see in our daily lives are offline UPSs, online UPSs, and line interactive UPS. An offline UPS switches over to the battery when the input voltage falls below a certain threshold. It includes a small delay, which may be 15 to 20 seconds at max. In the case of an online UPS, on the other hand, the power is always connected to the battery, which is always connected to the mains. Therefore, it offers no interruption whatsoever. A line interactive UPS constantly monitors the power line and tries to switch over as soon as it detects some anomaly. Generators. Generators in any facility are there to provide backup power for longer durations and is often used along with the UPS. While a UPS offers a short term solution, a generator can provide a longer term solution and is essential for maintaining power in critical facilities. Dual power supplies. It involves equipping devices with two independent power sources, allowing for one to take over if the other fails. This is very common in servers, network switches, and other critical IP equipment. It also allows the infrastructure to share the load. Power distribution units or PDUs. They are devices that distribute electrical power to multiple devices from a single power source. They are essential for managing power distribution in data centers and other environments with high power density. They also offer remote controlling and monitoring capabilities. Replication. Replication refers to creating copies of data in multiple locations to ensure data availability, consistency, and redundancy. SAN replication. A SAN is a dedicated high speed network of storage devices. SAN replication is a method of replicating data between SANs, and it can be performed synchronously or asynchronously depending on the required balance between data consistency and performance. A SAN replication ensures that a backup copy of data is always available in case of primary storage failure. We can also replicate data between two SANs, which is known as SAN to SAN replication. VM replication. VM replication involves copying the state and data of virtual machines to another location, ensuring that VMs can be quickly restored in the case of failure. Instead of saving the new VM over and over again, some softwares allow only the changes to be replicated inside the copies. On-premises versus cloud redundancy. In terms of on-premises redundancy, we need to maintain backups and replication systems within the organization, which can be a tedious task. When we talk about cloud redundancy, we can use cloud services for data replication and backup instantly. Cloud connections are generally slower as compared to on-premises systems, but on-premises systems involve significant capital expenditure as compared to a cloud model, which may have a subscription-based or pay-per-use model. Data on the cloud may be accessible to others as well, as compared to an on-premises system, where the data is accessible only to the organization's employees. Backups. File backups. File backup involves copying individual files and directories to a backup location. This type of backup is useful for preserving specific data without copying the entire system. We can have selective backups, which allows users to choose specific files or folders to backup, or we can have granular control over the system, which facilitates the restoration of individual files without needing to recover the entire system. Incremental backup. Incremental backup captures only the changes made since the last backup, whether it was full or incremental. This type is efficient in terms of both time and storage space. All increment changes are stored and then added onto the last full backup, which means that there is a low backup time but a high restore time. Differential backup. Differential backup copies all the changes made since the last full backup. This method is a middle ground between full and incremental backups. Backups that have changed in the last full backup are accumulated inside this type of backup, and each differential backup grows until the next full backup is performed. This kind of backup requires moderate backup time and moderate restore time. Backup media. Backup media refers to the location where a backup is stored. It may be an HDD, an SSD, a CD, DVD, or Blu ray, or tape drives. It may even be a cloud storage service. NAS or Network Attached Storage. It is a network storage solution that provides centralized and scalable backup options. It offers file level storage, which means for changing a single thing in a small file, you need to change the whole file altogether. It is cost effective but has low performance as compared to a SAN. That said, it is easier to set up and manage than a SAN. Other backup types often include cloud backups and image based backups, which capture the entire desktop or virtual machine. Backup locations. A backup may be stored online, which is most likely a cloud storage service. Data is stored on remote servers managed by a cloud service provider and can be accessed from anywhere with an internet connection. For an offline backup, data is stored on physical media such as external drives or tapes. It offers protection from online threats and internet outages, but requires physical management and transportation for off-site storage. Resiliency. Resiliency refers to the ability to withstand and recover from disruptions, ensuring continuous operations and minimizing downtime. It ensures data integrity, system availability, and operational continuity. Non-persistence. Non-persistence refers to the practice of using temporary environments or instances that do not retain changes after a session ends. This approach is commonly used in virtual desktop infrastructure or VDIs and cloud environments to enhance security and manageability. It also minimizes the risk of corruption. High availability ensures that the systems and servers operate on time, even in the event of failures. It involves redundant mechanisms to provide continuous service. An aspect of high availability is low to ensure that no single component is causing a bottleneck. Order or restoration is a sequence in which systems this prioritizes and ensures that the most services are brought back online first to minimize business impact based on the importance and interdependencies of the systems. Diversity. Diversity involves using varied technologies, vendors, cryptographic methods, and controls to enhance resiliency and security. By avoiding reliance on a single point of failure, diversity helps us manage risks or mitigate risks. Technology diversity. In technological diversity, we use different operating systems, hardware, and software to reduce the risk of single vulnerability which can affect all systems. Vendor diversity. We utilize multiple vendors for hardware, software, and services to avoid dependency on a single supplier. It allows us to maintain flexible contracts to switch vendors if necessary. Cryptographic diversity. Using different cryptographic algorithms to protect data reduces the risk of a single algorithm being compromised. For doing so, we can implement diverse key management practices to enhance security. Control diversity. In control diversity, we use multiple layers of security controls, which can be firewalls, intrusion detection systems, and antiviruses, to protect against various threats. Embedded systems. Embedded systems are specialized computer systems that are integrated into larger devices or systems to perform dedicated functions. These systems are essential in a variety of applications, ranging from industrial control to consumer electronics. They are often cheaper than the complete computer systems. System on chip or SoC. An SoC integrates all components of a computer or other electronic systems into a single chip. This includes the memory, the GPU, the CPU, the input output ports, and storage, providing high efficiency and performance in a compact form factor. SoCs are generally small, cheap, and very power efficient. FPGA or Field Programmable Gate Array. An FPGA is a type of integrated circuit that can be configured by the customer or designer after manufacturing. FPGAs offer flexibility and high performance for specific tasks. They also allow parallel processing. SCADA and ICS. SCADA, or supervisory control and data acquisition, allows us to gather and analyze real-time data. ICS, or industrial control systems, allows us to control systems used to operate and or automate industrial processes. Both these tools provide continuous data acquisition and control. Smart devices and IoT. Smart devices and IoT refer to the interconnected devices that can communicate and exchange data to perform automated tasks and improve efficiency. They use Wi-Fi, Bluetooth, or other protocols to connect and communicate. They use sensors to collect data from the environment or user input and perform tasks based on data analysis and user preferences. Specialized devices. Specialized devices are embedded systems designed for specific applications, offering tailored functionality and high performance. Some examples of specialized devices are VoIP or voice over IP communication over the internet, and HVAC which manage heating, ventilation, and air conditioning in buildings. Real-time operating system or RTOS. An RTOS is an operating system that is designed to process data as it comes in with minimal delay. They are crucial for applications requiring timely and deterministic responses. Surveillance systems. Surveillance systems use embedded systems for monitoring and security purposes, capturing and analyzing video and audio data. They provide 24/7 surveillance. But one issue with surveillance systems is that the hardware in surveillance systems is generally hard to replace. Embedded system communications. 5G. 5G is the fifth generation of mobile network technology, offering high speed, low latency communication suitable for a wide range of applications, including embedded systems. It provides data rates up to 10 Gbps, enabling rapid data transfer, and gives 1 Gbps on average. It is quite useful in IoT devices since it enhances connectivity and data exchange in smart homes, devices, and cities. Subscriber Identity Module or SIM card. A SIM card is a portable memory chip that stores unique subscriber information and security keys, enabling us to connect to the mobile networks. A SIM card can be easily transferred between devices. Narrowband. Narrowband is a low-powered wide area network or LPWAN technology designed for IoT devices that require long battery life and broad coverage. It has low power consumption, that means it extends the battery life of all connected devices. It offers extensive range including includes deep indoor penetration and reduces the cost of device connectivity and deployment. Baseband. Baseband refers to connectivity via. It can be used both ways but only one at a time. Zigbee. Zigbee is a specification of high-level communication protocols using low-power digital radios based on the IEEE 80.15.4 standard for personal area networks or PAN. It is ideal for battery-operated devices since it has a low power consumption, and it supports mesh topology, enhancing network reliability and range. Constraints on embedded systems. Power. Most IoT devices operate on a battery, and these batteries have a limited battery life. Hence, these batteries may need regular maintenance or need to be replaced. Computing. Embedded processors often have a low computational capability compared to a general purpose CPU. Both RAM and storage capacity are usually constrained, limiting the complexity of software applications. Network constraints. IoT devices often work on Wi Fi, and wireless networks often have limited bandwidth, which can affect data transmission rates. Network can be sporadic, particularly in remote or public environments. On top of that, network latency can impact the real time performance of applications. IoT devices also have less options for connectivity compared to the other PCs or devices. Cryptographic constraints. Since IoT devices have bad computing power, they cannot perform complex cryptographic operations. This may lead to the data being manipulated or leaked. Patching difficulty. IoT devices are meant to operate independent of human actions, which leads to a lack of physical access or network connectivity access, making it difficult for updating and patching softwares. This can also lead to non compliance. Authentication constraints. Many embedded systems lack a user interface for complex authentication methods, and implementing strong authentication can be resource intensive, which IoT devices are not able to support. Range constraints. This refers to the inability of embedded systems to do another task that they are not built for. Since there are no additional resources, embedded systems do not have any range of what they can do. They are only good for particular tasks. Low cost components. Since most people go for low cost in an embedded system, it can lead to high failure rates or lower durability. Since most embedded systems run a real-time OS, they want consistency in system performance, which cannot be there for if in cases of bad quality components. Implied trust. Embedded systems may ship with default settings that are insecure. The problem lies that we are unable to change these settings due to limited access to hardware and software. Physical security controls. Barricades or bollards. Barricades and bollards are physical barriers used to prevent unauthorized vehicles access and protect buildings from vehicular attacks. They are constructed from robust materials to withstand impacts from vehicles. Access control vestibules. Access control vestibules, also known as man traps, are secure entryways that require verification before granting access to the inner area. They prevent tailgating and unauthorized entry. Alarms. Alarms can detect unauthorized access or environmental hazards and alert the employees accordingly. Signs. Signs provide clear information and warnings to individuals about security policies, restricted areas, and safety procedures. Signs can also be used as a deterrent for any insider threats and people who want to gain unauthorized access. Signs can also be used to convey emergency information. Video surveillance. It involves the use of cameras to monitor and record activities in and around a facility. It allows for live viewing of security footage and provides evidence for investigations. Industrial camouflage. Industrial camouflage involves designing facilities and infrastructure to blend in with the surroundings, making them less noticeable to potential threats. We often use industrial camouflage for key assets, guards, and access lists. It involves using security personnel and in controlled access lists to manage entry and monitor activities. It provides a physical deterrent and rapid response capability since there is a human presence. Biometrics. Biometrics uses biological traits like fingerprints, iris patterns, and more for authentication. It provides high security through unique biological characters and reduces the risk of credential threat or sharing. It also simplifies the authentication process. Door access control. Door access control systems use electronic locks and authentication mechanisms to secure entry points. All the doors or entries that use door access point have locks built into them, which can be used to record and monitor events. Cable locks. Cable locks are physical locks put on cables to prevent theft or unauthorized movement of cables. It can be used on a variety of devices or equipment. USB data blocker. A USB data blocker is a physical device that does not connect the data pins of the USB port. This allows us to prevent USB jacking. Proper lighting. A proper lighting helps us in better surveillance and reduces the likelihood of criminal activity by increasing visibility and acting as a deterrent. Fencing. Fencing is a physical boundary that defines property boundaries. It prevents access to sensitive locations, but adding a boundary would make it seem like there is something hidden there, which makes it not work well with industrial camouflage. Fire suppression systems. These systems detect and extinguish fire in order to protect people, property, and data. They use sensors to identify fire hazards and deploy agents, which may be water, gas, or foam, to suppress fires. Sensors. Sensors detect various physical conditions, may it be motion, temperature, or humidity, and trigger appropriate responses. Some famous examples in an industry are smoke detectors, temperature sensors, and motion sensors. Drones. Drones are used for aerial surveys and monitoring of a large or difficult to access area. They are used for surveys, damage assessment, and evidence capture, and more. A Faraday cage is an enclosure that blocks electromagnetic fields to protect sensitive electronic equipment from interference or eavesdropping. The downside is that we cannot access or communicate from anyone outside the building while we are inside the Faraday cage. Screen subnets or DMZs. DMZs are network segments isolated from an organization's internal network to enhance security. They have limited exposure to external threats. Protected Distribution System or PDS. A PDS is a secure physical pathway for electrical and data cables, protecting them from tampering and eavesdropping. Air gap. Air gap refers to the practice of physically isolating a computer or a network from any other network, especially the internet, to enhance security. It prevents remote hacking attempts and malware injections, and it requires physical media such as a USB drive for file transfer. Vaults and safes. Vaults and safes are both used for securing data, documents, and other valuable properties from theft, manipulation, and natural disasters. Vaults are larger and cannot be moved or placed anywhere else. Safes, on the other hand, can be moved or placed anywhere else and are relatively smaller. Hot and cold aisles. It is a layout design used in data centers to improve cooling efficiency in such a way that the hot air coming out from all the servers and devices is collected in one place. All that hot air is then vented out collectively at a single spot. Secure data destruction. Data destruction and media sanitization. When we need to throw away or reuse a hard drive, we need to make sure that the data can no longer be retrieved after being reused once. We also need to make sure that we meet legal and industrial standards for data protection. Protecting your garbage. It refers to protecting garbage, which may include discarded media and documents, to prevent data breaches through dumpster diving. In order to do so, it is recommended to use lock pins or incinerate the garbage. Physical destruction. It refers to breaking down storage media to ensure that the data can never be retrieved. We can use equipment such as shredders, crushers, and drills for the same. A famous process is for destruction of hard drives is called degaussing, which involves using strong magnetic fields to make sure that the drive can never be used again. Certificate of destruction. It is a document that certifies that data has been securely destroyed in compliance with relevant standards and regulations. It is often issued by professional data destruction services. Sanitizing media. We use this when we wish to reuse a media drive. In order to do so, we can either wipe the device or purge data from the device. Wiping the device involves deleting everything from the drive, while purging involves deleting only a portion of the data. Data security. While destroying data, we need to make sure that the data is unrecoverable. We also need to make sure that we can trust the third party responsible for the destruction of data.